presenting integration of slip detection and grip force control in an autonomous robot assembly task for space. This research is motivated by the long-term objective of establishing extraterrestrial habitats on the lunar or Martian surface, with robots performing autonomous assembly using in situ materials. These materials can often exhibit significant variability in their properties, frequently being fragile or brittle. Therefore, a gentle grasp is required while handling them, with the capability to increase the grasping force only when necessary, for instance, to prevent slippage during assembly tasks. In this study, we integrate slip detection and grip force control in a representative robotic assembly task. The slip detection module utilizes a long short-term memory LSTM-based neural network trained exclusively on simulation data, achieving a specificity and sensitivity of over 80% on test experimental data without any training on experimental data. This model enables the detection of linear slip based on the applied normal gripping force, allowing the robot to adjust its grip dynamically and avoid slippage. The experimental setup consists of a Ufactory X-arm robot, equipped with a FUTEC single-axis sensor mounted on its gripper. The representative demonstration task involves assembling blocks with magnetic connectors and pushing a heavy object to demonstrate the effectiveness of the slip detection model in detecting slip and taking corrective actions. The demonstration comprises 4 key phases: detecting and aligning with the black block, assembling the black block with the blue block, pushing a heavy object with the assembly and detecting slip, and taking corrective actions. Starting from the home position, the X-arm robot employs the YOLO object detection algorithm to accurately identify the position and pose of a randomly placed black block. The robot then executes a gentle grasp, sufficient to just pick the block. To perform the assembly, the robot aligns itself with the blue block, completing the task using magnetic connectors without the need to alter the grasping force. However, pushing a heavy object necessitates a stronger grasping force. Initially, the robot fails in this task due to insufficient grip. The LSTM-based slip detection model identifies the slip by analyzing changes in the normal gripping force. Upon detecting the slip, the system increases the grasping force, enabling the robot to successfully push the heavy stack. This demonstration highlights the efficacy of the slip detection model, showcasing its potential for managing in situ materials in autonomous assembly operations on lunar surfaces.